Multimode fibers. Multimode fibers support systems that operate in shorter wavelengths than single-mode systems, so the signals attenuate faster and limit their distance reach. Dispersion issues in multimode fibers also limit bandwidth, limiting their use to applications of lower data transfer speeds and bandwidth than single-mode systems. Due to these limitations, multimode fibers are typically used in local area networks in premises or campuses. However, specific data center applications combine multiple fiber strands in parallel arrangements to achieve greater capacity than single multimode strands. Multimode fibers have larger cores than single-mode fibers, enabling light to travel in multiple trajectories through them. Though the core diameter sizes of typical multimode fibers used in communications are 50 and 62.5 microns, there are other variants of multimode fibers that are ruggedized with plastic claddings known as plastic-clad or hard-clad silica fibers with core sizes of 200 microns. Also, there are fibers that are fully made of plastic, known as plastic optical fiber or POF, with core sizes close to 1 mm. The larger area of the cores in multimode fibers make them more tolerant to misalignment than single-mode fibers, reducing installation complexity. The larger cores in multimode fibers enable light signals to travel in different trajectories or modes simultaneously. This results in more light being transmitted through these fibers, which could be advantageous when using lower-cost transmitters like LEDs. However, as different modes reach the signal receiver at different times, these cause signal degradation known as modal dispersion. Multimode fibers are made with different designs known as step index and graded index fibers. Step index multimode fibers are built with a slight refractive index differentiation between the core and the cladding to make light modes bounce of the core to cladding boundary as these travel through the fiber. On the other hand, the cores in graded index fibers are built in layers, increasing refractive indices gradually from the core's center out to the edges. This technique of layered cores in graded index fibers forces light modes to follow more similar trajectories as these travel through the fibers to reduce modal dispersion. Though chromatic dispersion affects both single-mode and multimode fibers, typical communication multimode fiber links are not long enough for these to require field testing. Multimode fibers have evolved over the last decades, with newer innovative types that support higher bandwidth, speed, and even multiple wavelength transmission. In just over 2 decades, we have seen multimode fibers evolve from OM1 all the way up to OM5. Whereas OM1 fibers have a core diameter of 62.5 microns, more recent ones have smaller 50-micron diameter cores to support more efficient laser-based transmitters called VIC cells for speeds in rates of gigabits per second. These fibers are commonly referred to as laser-optimized multimode fibers. OM5 fibers, also known as wide-band multimode fibers, have similar characteristics such as core size and distance limitations as OM3 and OM4 fibers. However, OM5s are designed to support multi-wavelength transmission over the same fiber to achieve increased bandwidth and speed for data center applications. Ruggedized variants of multimode fibers include plastic-clad or hard-clad silica fibers that have a core diameter of 200 microns. These are used in some local area networks or for industrial environment applications requiring rugged cable designs. There are also fibers that are made of plastic, known as plastic optical fibers or POF, with core sizes close to 1 mm and an outside layer of only 20 microns. POF fibers are very limited in distance reach, but are useful in applications like home entertainment or automobile audio systems.